in this problem, we're studying the change in heat loss due to radiation for penguins. We're considering the penguins that are standing separately to check how much energy they're losing. And then these penguins, they huddle, so they stand side by side, basically to warm each other up. And this happens basically because when these penguins huddle, the area that is exposed to the environment becomes less. So we're told that to withstand the harsh weather of the Antarctic, emperor penguins, they huddle in groups. We assume that a penguin is a circular cylinder with a top surface area, A equals 0.34 meters squared. And the height of this cylinder is 1.1 meters. So each penguin is considered to be a cylinder, basically. A is 0.34. This is the area of the circular face. And the height is 1.1 meter. Let PR be the rate at which an individual penguin radiates energy to the environment through the top and the sides. So PR is the radiated energy rate from one penguin to the environment. So if I have 10 penguins that are well separated, the amount of energy lost by n separate penguins will just be P total equals n times PR, right? Now, if the penguins huddle closely to form a huddled cylinder with top surface area NA and height h, the cylinder radiates at the rate pH. So now the penguins are huddled together, so it's as if they are standing together, all of the cylinders, and we consider them to be all forming one big cylinder of the same height as the separate cylinders, but the surface area, the top and bottom areas are going to be more. So essentially, I have n cylinders combined into one big cylinder, right? So this is for huddled penguins. And the energy lost by n penguins huddled together is pH. Now, what's the difference between the two cases? It's essentially in the surface area, right? For one single penguin, we can write the radiation energy rate to be sigma, which is the Stefan-Boltzmann constant, E, which is the emissivity, the surface area, and T power 4, which is the temperature of this penguin. Whereas for n separate penguins, this is going to be n sigma E A T power 4. For the huddled penguins, we will have sigma E, a new area, times T power 4, where T is like the same. So what is the question? If n equals 1000, what is the value of the fraction pH over NPR? What we want basically is the ratio of the energy emitted by the huddled penguins to the energy lost by the penguins if they were separate. So we want basically to see how much this is going to differ, how much energy is going to be saved basically if these penguins are huddled. So I'll just substitute for a start the formula that I have written here. And you can see how essentially we just need the ratios of the areas because everything else is going to cancel out. So what remains is to just try to find the ratio of the areas. So I'm gonna check the area here. Like we said, for the radiation energy transfer, this is the surface area. Remember, for energy transfer, we have a formula for conduction and a formula for radiation. For convection, we did not associate any formulas because it's quite sophisticated with a lot of fluid dynamics for the flow of the air layers or the liquid layers from one part of the fluid to another during heat transfer. So for conduction, we have this formula P, which is Q over T is equal to Ka delta T over L. L is the distance through which heat is transferred, whereas A is the cross-sectional area. So if I have basically the cylinder itself and heat is transferred in this direction, then this is L and A is the area of the circle. Whereas for radiation, the formula is sigma E A T power 4. Delta T here is T hot minus T cold, essentially. T here is the temperature of the object. And A is the surface area. So here, for example, in this example, in the conduction example, the area is going to be just pi r squared. Whereas if the same cylinder is emitting heat by radiation, this is going to be from all of the faces. So A is going to be the surface area, which is 2 pi r L. So that's basically something to just be aware of, the difference between the areas and the two modes of heat transfer. So here the area is essentially, again, going to be 2 pi RL. By the way, we should also add the faces because energy is radiated from the circular faces as well. In this question, namely, we are told that the energy radiates to the environment through the top and the sides. So they asked us to neglect the bottom face. This is one mistake that many students would do, to take the area to be everywhere with the top and bottom faces. But the problem asks us to neglect the bottom face. So I will not take the bottom face, and I will put the area for the big cylinder to be pi r squared. We are given the new area. We are told the top face has an area NA, so I can directly use that. So for the top face, I'll write NA. This is the area of the top face, plus 2 pi r, was it L or H? Let's check the height. So the height was given as H, so I'll leave this H. Whereas for the bottom, for the separate penguins, I have the area is going to be A alone plus 2 pi, let's name this R prime, RH. Now I don't have the radius, rather I'm given the area itself. But I know this is pi r squared, so I can say that R will be radical A over pi, right? So this will be NA plus 2 pi radical A over pi times H. Actually, this will have times N because it's the huddled cylinder. For the big cylinder, the area is A prime is equal to NA for the top face, right? Which is, again, pi R prime squared. So R prime is going to be radical NA over pi. This is the radius of the big cylinder when the penguins are huddled together. So I just substituted R prime by NA over pi. And in the denominator, I have N into A plus 2 pi, the radius for the separate penguin. So this is, for this case, the radius is radical A over pi. times H. The rest is just substitution. We have the numerical values for everything. N is 1000. A was given to be 0.34 meters squared plus 2 pi radical. As a matter of fact, I can simplify the pi's. I will have 1000 times pi times 0.34 times 1.1 over 1000 times 0.34 plus 2 pi radical 0.34 over pi times 1.1. So you can find the ratio. I think it was 0.18. I'm not very sure. Something like that. But what does this tell me? It tells me the energy radiated when the penguins are huddled is 0.18 or 18% of the energy radiated when the penguins are separated. So the penguins saved quite a lot of energy, namely 82% of the energy they are losing when they huddle together. In part B, they ask us by what percentage does huddling reduce the total radiation loss? So we want by how much the energy lost was reduced. So the energy is reduced by 100 minus 18%, which is 82%. Any questions?